Okay, so we're going to start talking about technically, I think it's chapter 8 at this point in time. So, in a previous edition of the book, there were less chapters to deal with, I guess. I think this was chapter 7, but now I think technically quantum mechanics and dealing with the information covered for quantum mechanics is in chapter 8, okay? So, we've been dealing a lot with stoichiometry, and then we just talked about energy. And so this is going to be our first kind of foray back into some of the basic ideas behind bonding that we have, or basic theories that make up our theories of bonding. And we start that by dealing with something called quantum mechanics, okay? So if you guys go back in time, back to, I think, chapter 2, we had dealt with the atom, right? So we had an atom. We kind of defined what was made up in the atom. And so the atom we knew contained a nucleus, right? So we knew that the atom consisted of a nucleus. And in the nucleus, we had our protons, right? So we had, again, our protons, which is what I abbreviate this guy, a P with a little superscript plus. And we also had our neutrons, right? And so these guys, again, were our neutrons. And there are a couple of characteristics about protons and neutrons, right? So protons were our positively charged particle, right? They also contributed mass to the atom. And neutrons were electrically neutral, right? So they had no charge overall, but they also contributed mass to the atom, okay? And so if we had positive charge, we have a neutral charge. Both of those are contributing mass. The other subatomic particle that we had was the electron, right? And the electron was essentially the first one to actually be discovered, okay? So now some characteristics of the electron were, number one, it was negatively charged, right? So it's essentially balancing the positive charge of the proton. And then comparatively to the proton and the neutron, electrons essentially had no mass, right? So again, that's incorrect. They do have mass, but the size of the electron compared to the proton and the neutron is pretty incomparable, right? So essentially, the presence of the electrons was contributing no mass to the overall mass of the atom because the protons and the neutrons were so much more mass intensive, or massive, I guess, okay? Okay, so we knew that the protons and the neutrons were in the nucleus, and then we knew that the electrons were there, and we had kind of a theory about where they were, but this is essentially, this chapter is going to deal with this kind of question about, number one, where are the electrons with respect to the atom, right? And then what are they doing with respect to the atom and how they're behaving, etc. And again, long term, what this is going to help us do is kind of formulate different ideas and theories with respect to bonding. Because when we get into things, when we get into bonds and atoms coming together to create bonds, it's going to be because of attractions between electrons, and then attractions between electrons and other atoms. Okay, so we kind of want to know, number one, where are the electrons at, right? And then number two, what are they doing? Okay. Now, the answer we're going to get is going to kind of be fairly unsatisfactory. And this chapter is going to tell us or explain to us why this answer is unsatisfactory. So the overall theory that tells us what electrons are doing and where they are in the atom is what we call quantum mechanics. Okay, and so quantum mechanics as a theory was developed in like the early 1900s, right? And it was developed by a lot of very, very, very intelligent people, including Albert Einstein, Niels Bohr, etc. Lots of people helped contribute to the development of this theory, okay? So up until the beginning of the 20th century, up until the beginning of the formulation of quantum mechanics as a theory, all physics and all physical phenomenon had believed to be very deterministic, right? So what does deterministic mean? So for example, if we were to think of a ball, like, so let's say some sort of baseball, right? And you were to throw that baseball into the air, we could predict with fairly certain probability where that baseball would land, right? If we knew the factors that were working on it, so the forces, the wind resistance, etc., the trajectory at which we threw it at, the velocity that it was going, we could predict with fairly decent certainty that it would land, let's say, 100 yards away from us, okay? Okay, so that's what we mean by deterministic. With knowing various features and various characteristics of whatever thing we're dealing with, we can kind of predict where it's going to end up. Okay, so the problem with quantum mechanics and the problem with electrons in general is the fact that, number one, electrons, again, are very small, right? And so when we go down to the very tiny world of the electron, matter behaves a lot differently than it does on what we call the macroscopic world that's around us. Okay, so the macroscopic is our big, it's our baseball, it's our basketball. The microscopic world, again, microscopic world of the electron, again, behaves very differently than our macroscopic world that we live in, right? So if we were in the tiny microscopic world of the electron and we shot it, right, or we threw it, if we could do that at a certain velocity and a certain trajectory, etc., unfortunately, we wouldn't be able to know exactly where it was going to land, and we wouldn't be able to predict exactly where it was going to land. Instead, what we'd be given is some sort of probability distribution about which we were kind of certain that it was going to land, right? So we could say maybe with 90% certainty, we think it's going to end up about right here, right? So that's what we would call indeterministic. And what we're going to be left with in deterministic, what we're going to be left with respect to this small microscopic world of the electron, is this kind of indeterminate state of matter, right? We're not going to be able to know with exact certainty where the electron is, where it's going to be. Instead, we're going to be just kind of given an overall probability of where we think it's going to be in an atom. And so that was very disturbing to a lot of people. The fact that we could only really describe the behavior of electrons in terms of probability didn't really sit well with some people. Okay, so that's what quantum mechanics essentially gives us. It gives us this very indeterminate structure of matter. The only problem is, so again, people aren't super happy with that. The problem with that is the fact that quantum mechanics is one of the most successful theories that has ever been developed in science, right? So in terms of theories and in terms of things proving theories, quantum mechanics and the quantum mechanical model of the atom is the most successful thing that has been developed. Okay, so people are unhappy the fact that we can't know necessarily where electrons are at. We can only be given probabilities. That sucks, but it's going to be how it is because, again, this is a very, very, very strongly experimented on and strongly proven theory. Okay, so long term, what we're going to get out of quantum mechanics, we're going to know where atoms or where electrons are at in atoms. It's going to help us explain the structure of the periodic table and why we actually see certain chemical reactivities with respect to various elements. It's also going to explain the behavior of bonding and chemical bonding. So all matter consists of bonds for the most part. We haven't talked about bonds, but quantum mechanics is going to kind of form the basis behind how we're going to understand bonding. So before we actually start talking about quantum mechanics as a theory, we actually first have to go and talk about light. And so hopefully long term, this relationship between quantum mechanics and light will be made apparent. But we're first going to start talking about light. All right, so light, what is light? We don't really deal with light that much yet thus far in our chemical career, but light is a form of electromagnetic radiation. Right? So what is electromagnetic radiation? So essentially electromagnetic radiation is composed of perpendicular oscillating electric fields, so electric fields as well as magnetic fields. Okay, so an electric field is a region of space where an electrically charged particle experiences a force, whereas a magnetic field is a region of space where a magnetized particle experiences a force. So electromagnetic radiation consists of these perpendicular oscillating electric and magnetic fields, and they're oscillating or moving in whatever direction that they are going. Okay, so light, again, is just this electromagnetic radiation. Okay, so if that is what light is, then light is essentially can be at least thought of as a wave, right? So again, it's these perpendicular oscillating fields, these waves. So we are going to right now already assume that light behaves as if it were a wave. There are a couple of different characteristics that we need to talk about with respect to waves. So one way that we can characterize a wave is via what is called the amplitude of the wave. So if we looked at our little wave over here, right, so a little wave in little figure A here, the amplitude of the wave is given as the distance from the trough to what we're going to call a node. So the zero axis here is what we call a node, and, oh, pardon me, this is what we call a crest, not a trough, okay? So again, the amplitude is given as this distance between a node and a crest, or it can be the exact same thing between a node and what we call a trough. I think that's how you spell trough. So that's one way that we can categorize a wave, is how high it is, its amplitude. Another way that we can categorize a wave is via what's called its wavelength. So the wavelength is going to be the distance that essentially a wave travels, right? So we can measure this from a crest to a crest, we can measure it from a trough to a trough, or we can measure it from a node to a node. Okay, so again, the wavelength is just the measure of distance traveled by a wave, and we would usually measure this in terms of some sort of distance or length measurement, which would be something like a meter. Okay. All right, so another way that we can categorize a wave as opposed to wavelength is something called frequency. So the idea behind frequency is that this is going to be the number of waves, or the number of complete wavelengths that pass a given point in a period of time. Okay, so what we could do to measure frequency is we could sit at this point and we can essentially measure how many full waves get through this point as they're moving in this direction in a given period of time. And so frequency is going to have units of events per time, right? And so that time is usually in S, and so this is usually given in units of S to the -1, so this is again 1 over S. This inverse S, this inverse seconds, this has an actual unit itself. This is what is called a hertz. It's given as this guy, this Hz. So if you deal with physics, you deal with frequencies a lot, you probably have heard of what a hertz is. Okay, so if you think about waves and you think about their various characteristics, so amplitude, wavelength, frequency, if we wanted to think about the energy of a wave, there are two different things that are going to go into the total energy of a wave, right? So let's say that you're out in the ocean and a wave hits you, right? The larger the wave, right? So the larger the wave, which is going to manifest itself as the amplitude. So the larger the wave, the larger the amplitude. If you think about getting hit by a big wave, the more energy you're going to have in that wave, right? So larger waves, larger amplitudes lead to more energy. So amplitude and energy are going to be directly proportional to one another. Another way we can think about energy of waves is if you get hit by a bunch of waves in very rapid succession, then they're going to have more energy as well, right? So very rapid succession waves would have a large frequency, right? And so we utilize this little Greek letter, this guy, it's called nu. We utilize this frequency to represent, or this Greek letter nu to represent frequency. So large frequency also leads to more energy, and so frequency is also going to be directly proportional to energy when it comes to waves. So energy of a wave is going to be given by its amplitude as well as its frequency. All right, so we've already talked about how light, electromagnetic radiation, is going to behave like a wave, right? So now that we have some characteristic properties of waves, how does that actually manifest itself with regards to light? So with light, the dimness and brightness of light is how we determine what the amplitude is, or this is how the amplitude kind of presents itself. So the brighter the light, the higher the amplitude. And then the dimmer the light, the lower the amplitude. And then how does frequency or wavelength, which again are going to be related to one another. How do they manifest themselves in our light? So they're going to essentially appear as different colors. So different color light have different wavelengths and different frequencies. So for example, red light has its own given wavelength, its own given frequency. Yellow light is a little bit of a smaller wavelength, a little bit larger of a frequency, and then blue light is one of the more energetic ones. It's going to have a very tiny wavelength comparatively and a very large frequency. Okay, so I've hinted at the fact that there is a relationship between frequency of light and its wavelength. So I already defined this little Greek letter. This guy is nu, and again, it's what we represent with respect to frequency. So frequency is given by this guy. This guy is lambda. This again, another Greek letter, and this is how we represent wavelength. Okay, so just want to make sure I write out, when I write out nu and lambda, we're both talking about the same thing. Okay, so nu is representing frequency and lambda is representing wavelength. Okay, so I've mentioned these again are characteristic properties of waves, that these guys have a relationship, right? So if we think about frequency, I've already talked about its units having some sort of number of events per unit time, so something per second. So something per second, so frequency is usually in something of inverse seconds. And then wavelength, we also talked about, had units of distance, right? So meters. So if we multiply these two things together, we're going to end up with something like meters per second, which ideally you should represent, or you should notice as being some sort of speed or velocity, if you will. Okay? So the relationship between frequency and wavelength is essentially the speed of whatever wave we're looking at. And for electromagnetic radiation, this is speed. This is the speed of light. Okay, so speed of light is a constant. It is moving at a constant speed, so that speed is 3.0 times 10 to the 8th meters per second, which is very, 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 very fast. All right, and so all electromagnetic radiation moves at this exact same speed. And so we can kind of rewrite this in this little equation, right? So this is going to give us what our frequency is. This guy is going to be our speed of light, which is a constant again, 3.0 times 10 to the 8th, and this is going to be our wavelength. Right, so if I know the frequency of light, I know it's light, and I know my constant speed of light, then I can calculate the wavelength of light and vice versa. So you should also note here that frequency is inversely proportional to wavelength, right? So the larger the wavelength, the smaller the frequency. The smaller the wavelength, the larger the frequency. So these guys have an inverse relationship with respect to one another. So when we think of light in general, we always think of just like visible light, the actual light that we see. But with respect to all of the various wavelengths of the electromagnetic spectrum, visible light essentially constitute a very, very, very small fraction of those wavelengths, right? So we have on this slide the entirety of the electromagnetic spectrum, right? So this goes from things like gamma rays. Gamma rays have very high frequency, very tiny, tiny wavelengths. So we start up here at very high frequencies, very small wavelengths. And then we go down after gamma rays, we go down to X-rays. So these have, again, smaller frequencies, larger wavelengths, ultraviolet. And this tiny little region in here is the visible spectrum, infrared, microwave, and radio wave, okay? Just as a reminder, there is a relationship between energy and frequency, and energy is going to be directly proportional to frequency. So the higher the frequency, the more energy these various wavelengths of light have, right? So up here at the top, we'll have the most energetic. So gamma rays are the most energetic, and then as we move down to the bottom, radio waves are the least energetic. Okay, so that kind of makes sense, right? So these guys up here, gamma rays, X-rays, UV rays, these guys all have enough energy to potentially ionize your biological molecules, which can lead to long-term bad effects, things like cancer, etc. So gamma rays we usually associate with radioactivity, and that's usually a bad thing. Gamma rays are produced by radioactive decay. Also X-rays, so we will expose ourselves to X-rays whenever we need an X-ray, but what do they do to the remainder of your body? They usually cover it with some sort of lead plate, so the remainder of your body doesn't actually get exposed to those X-rays, so we try to limit our exposure. And the same thing with ultraviolet, right? So we are exposed to ultraviolet light all the time, but we tend to try to minimize its damage by using things like sunscreen, etc., so that we long-term don't damage our biological molecules, don't get skin cancer, okay? Okay, so after these guys, so these are the most energetic, and they have enough energy that could potentially damage your biological molecules. After that, we move into visible. So visible, going from the smallest wavelength, which is violet, to the largest wavelength, which is red light. So it's violet, blue, green, yellow, orange, red, right? And so if we want to go into reverse, the visible spectrum is usually given by Roy G. Biv. So Roy, red, yellow, red, orange, yellow, green, blue, indigo, and violet. And so then as we move down, we've got infrared, we've got microwave, radio wave. So these guys have very, very large wavelengths, so very small frequencies. And they are not capable of doing anything to your biological molecules. They are not energetic enough to damage anything, right? So this is why we use them frequently in things like cell phones and then our various FM and TV frequencies. All right, so let's go ahead and do a question, right? So this is asking for the wavelength in nanometers of red light that is emitted by a barcode scanner that has a frequency of 4.62 times 10 to the 14th. So this is going to go back to our relationship between wavelength and frequency. So frequency times wavelength, so nu times lambda, is equal to the speed of light. And so, again, speed of light is a constant, 3.0 times 10 to the 8th meters per second. You'll have the frequency, right? They give you the frequency. You'll be solving for wavelength. This will be your unknown. And the only thing to note here is that the speed of light is given in terms of meters, right? But they want you to, I guess, denote this wavelength in terms of nanometers. Okay, so there's going to be a conversion step between meters and nanometers. Just as a reminder, 1 nanometer is equal to 10 to the minus 9th meters. So the nano is the minus 9th. But I'm going to go ahead, so this will be actually on the video assignment quiz, so go ahead and calculate this, and then hopefully you get the correct answer. Okay, so we'll go ahead and go over this one. So again, we do have this relationship where the frequency of light times the wavelength of light is equal to the speed of light, right? So right now we want to know what the wavelength is, so what this guy is, lambda, given that we know this and given that this is a constant, right? So what I'm going to do is I'm going to go ahead and solve for wavelength, right? Solve for lambda. So I'm going to do that, I'm going to divide both sides by the frequency, or nu, right? So we're going to get wavelength is equal to C over nu, or C over frequency. And then we can just go ahead and plug in the things that we know, right? So we've got our speed of light times 10 to the 8th meters per second. This is going to be divided by the frequency of light. So we have 4.62 times 10 to the 14th inverse seconds, right? And so when we do this, put in our calculator, so 3 to the 8th divided by 4.62 to the 14th. We're going to get a very, very, very small number. We put that in scientific notation. This ends up being 6.49 times 10 to the minus 7th meters, right? Because again, our units here are meters. The inverse seconds cancel the seconds here. this isn't really a great usable number, right? We've got a very small negative exponent here in scientific notation. So a better way to write this would be converting to nanometers, right? And so what we're going to find is like any type of visible light is usually in the 100 nanometer type range. So when we convert this guy to nanometers, we end up with 649 times 10 to the minus 9th meters, which is the 10 to the minus 9th is the nano. So this is 649 nanometers, right? And so we look up here, we find, oh, B here is 649 nanometers. So that is the correct answer. And again, this is characteristic of red visible light.